Dobré odpoledne všem, vítám vás na další akci College Google User Group. Tématem dnešní přednášky jsou nerelační databáze. Já už se o tuhletu problematiku zajímám nějakou dobu a když jsem poprvé slyšel o tom, že můžete mít databázi, kde nepotřebujete žádné pevné schéma, nemusíte dělat žádné migrace tabulek, tak jsem byl samozřejmě z toho nadšený a snažil jsem se co nejvíc prozkoumat, na jakém příštím projektu nějakou z těch nerelačních databází použít. Nějakou dobu jsem pracoval s Google Data Store a byla to beta samozřejmě, jako všechno ostatní v Google, když to začne. A velmi brzo jsem zjistil, že to s těma nerelačníma databázema není až tak jednoduchý. Sice všechno bylo bez schématu, ale bylo to na Google, byl tam vendor login, nešla ta databáze přesunout nikam jinam, bylo tam spousta omezení na dotazy a tyhle ty věci víceméně přetrvávají a to rozšiřování nerelačních databází postupuje pomalu a na spoustě míst je v podstatě nemyslitelný, že by takový nápad jako použít nerelační databázi vůbec byl schválen. Případně je nemožná představa, že by se použila vůbec nějaká jiná databáze než Oracle, to už záleží na tom, kde pracujete. Ale dneska teda máme šanci se o nerelační databází a konkrétně teda o databázi MongoDB dozvědět informace přímo od jednoho z jejich tvůrců. Ta přednáška bude teda probíhat v angličtině. Jo, a tím bych vám teda chtěl představit technického lídra vývoje MongoDB Alvina Richardse. Alvin,
So, thank you for inviting me today, and thank you for letting me speak in English. Almost zero. So, I am the technical director for 10Gen. 10Gen is the company behind MongoDB. I've spent the last 14 years working in Silicon Valley, and they sent me back to Europe to go figure out MongoDB in Europe and what we need to do here. So if I suddenly start speaking strange American terms, I apologize. My brain is slightly confused between thinking it's an American and being in Europe. It's all kind of crazy. All right, so this is kind of roughly what we're going to talk about, which is why MongoDB. We'll talk about schema design. Then we'll have a break for about 15 minutes so we can grab a coffee, or so I can grab a coffee. Then we'll talk about scaling. We'll have some time for question and answers. And apparently we're going to have a beer afterwards, right?
Yeah.
Okay. This is what I'm here for. No. Okay. So, why MongoDB? So this all came about through our founders. Our founder, Dwight Merriman, was the CTO and founder of DoubleClick. And DoubleClick was the first really big ad-serving platform that if you launched a web browser in about 1998 and you saw a banner advertisement, that was actually placed there by DoubleClick. And so Dwight's problem was this. They had a sort of a bit of an accident, which is they built this technology in 1997 using the state of the art. They had Sun servers, they had an Oracle database, and they had Java. And this is really, really cool stuff. Until they kind of ran out of space on their first Oracle and Sun box, and they went kind of, what do we do now? And so this led to a great deal of frustration from the developers, because how do you scale multiple databases? Well, what you do is you chop the data up between many machines, and then you have to figure out in your application code where that data is. And so kind of this led to a lot of frustration. Dwight kind of once estimated that 85% of DoubleClick's research and development budget was spent figuring out how to scale Oracle. This left 15% to add features. He did not think this was a good equation. And so like all good developers, what do? They found a way to patch up the solution. Don't try this at home, this is not my child. I found this picture on the web, honestly. Okay. The other thing that, as a startup company, DoubleClick didn't have is they didn't have this money tree. Now, there are a couple of companies still left in the world who have these money trees hiding in their basements, and they can afford to buy very big, exotic hardware to solve these problems. Most people can't afford that. And everybody, all of us in this room, are trying to avoid this big train wreck. And this big train wreck generally happens about 3 o'clock in the morning, where your cell phone rings or your pager goes off and your boss is on the phone going, the website's down or we can't conduct business. And then you try and wake yourself up with a few coffees or a Coke and try and code away and code away to get yourself out of this problem. All right. So who is 10gen? So we're the company behind MongoDB. We own all the copyright of the code. We employ the engineers who write the code, build out the features. We're a commercial company, so we sell support, consulting, training, a whole bunch of other stuff. We are a very traditional startup, so we are funded by some very nice people, Sequoia, Union Square, Flybridge, who gave us some money to go do this. This is one of the wonderful things of being in the Silicon Valley. There's lots of people who want to fund a really good idea. We think we have a very, very good idea. Our team came from Google, DoubleClick, Oracle, Apple, NetApp. We've got offices New York, Palo Alto, London, Dublin. We just opened Sydney a couple of weeks ago. If anybody wants to be a support engineer based in Sydney, there's job openings, if you ever fancy that. We're about 120 people, so this slide's already wrong. We're about 120 people or so. By the end of this year, we'll probably be about 200. So really, kind of, what are the challenges? Why did we go build this? Well, so people talk about big data. I kind of talk about big data as being more data than you can store on a single machine, because that's when you run into your problems if you're using Oracle or MySQL or Postgres. And so there are people who go, well, 200 gigs is a lot of data to them. To some people, a couple of petabytes is a lot of data. So it's all a relative thing. There are kind of new programming models. I mean, as we have started developing applications, we've been using object-oriented languages. Ruby, Python, Java, C#. And we've all been using this kind of object relational mapping layer, which takes this beautifully crafted object, and then we chop it up into lots of rows and tables and columns in order to persist it. And in order to actually rematerialize that object, we then have to do these kind of joins and other kind of crazy stuff in order to rematerialize that object. And I feel somewhat kind of responsible for that, because in 1987 I joined this company called Oracle, who were a tiny little company that nobody had ever heard of, and I spent 16 years working on the Oracle database kernel. And so I feel kind of guilty that some of this stuff happened, but it was really cool at the time, trust me. And so there's also a change, which is everybody wants to go into a more agile way of working. You don't want to do the classic kind of waterfall. What you want to do is you want to build something, get it in front of some people, figure out what works and what doesn't work, and quickly iterate on it. And if you've got a 2-weekly development cycle and you spend say 12 days of the 14 days arguing with the DBA to add 2 more columns, then that's not a very agile process. And the third point is that there's many new different hardware architectures out there. Amazon have done a great job establishing the fact that you can have on-demand infrastructure. You can simply swipe a credit card, you can spin up some instances, and as developers we can do this. We don't have to employ a system administrator in order to actually plug in networks or change disk drives or do operating system upgrades. So there's a whole new kind of sort of different deployment architecture. Now, with all the stuff that we're all using right now, what is the basic problem? Well, if you want to kind of scale your system, you first try running on a bigger box, and that will probably work pretty well. You get some more CPU, perhaps some more memory. The point that this starts running out, you then put a caching layer in front of it. It could be Memcache, it could be Redis, whatever the flavor of the month is. And then at the point where this starts running out, you then do custom sharding. Okay? So in order to scale, you've increased the complexity of your application tremendously. At the same time that you've increased the complexity, your productivity has somewhat declined because you've now denormalized your schema. You've had to remove joins because joins don't work well across database instances. You start removing transactions. So to scale currently, you end up with something that's very much more complex, and you spend most of the time doing all of this stuff rather than building features. So why do we exist? Well, we think there's three key things, which is agility, scale, and cost. And most people have got 2 out of 3 of these problems. Some people have got all 3 of them, which is I need a quicker way to develop that fits in with my development model. I need to be able to start off small, and if my feature is really, really popular, just add more compute into the cluster as I need it, rather than sitting down with a big spreadsheet and going to my boss and saying, I need $1.5 million in hardware, even before you've signed up the first customer. So you need to scale out as you need without actually having to take any downtime or change any code. And the final part is you want to do this as cheaply as humanly possible. Okay, so who uses MongoDB at the moment? Here's a whole bunch of use cases. Here's a whole bunch of logos. The kind of bottom line is that we have a wide variety of use cases with companies that you know. There's a whole bunch of companies on this that I can't tell you about. I'm sure some of you probably got devices of theirs in your pocket who have MongoDB deployed in production. But so all these guys are using MongoDB in production. And the final one is, why do you care as developers? So this data came from Indeed.com. Indeed.com aggregates job searches and job posts. And so their top job trends is number 1, HTML5. Number 2 is MongoDB. Number 3 is iOS. And then if you look at MongoDB versus the other NoSQL databases, this red line is MongoDB, this is Cassandra, this is HBase, that's CouchDB. So as a developer, I would care about this because this is saying to me that there's a lot of people looking for MongoDB skills. So if I get those MongoDB skills, there's a higher percentage of being able to find a good work or a good job position based on having those skills. Okay? Any questions on that?
What does it mean, no SQL market?
What does it mean? Good question. So there's a couple of ways that you can answer that. So some people say no SQL's bad. The other definition is nothing but, or SQL. And so what this really means is that if you take all the data that's being put in relational databases, then there are all of these other non-relational data stores. Everything from memcached, which allows you to store data, but it won't allow you to do it persistently, all the way through HBase and a number of other alternative technologies, MongoDB being one of those.
Okay, so that means like jobs where is storage, but there is no SQL. It's like that, because I'm wondering, there is HTML5 is first, and there is iOS, Android. Not everything is about storage.
So this top trends is the technology trends throughout Indeed.com's analysis. So we're looking at all technology.
It's like
and this is
global, everything.
Yeah, so this is just global technology as far as job posting is concerned, and this is relative to the other NoSQL technologies.
So those top trends are like global technology jobs?
Yes.
That's interesting.
Yes. I kind of think it's interesting.
Yeah.
All right, so now let's talk about schema design, because that's all the kind of, company marketing stuff. So what we're going to do is we'll look at some basic schema design and then look at some patterns. Okay, so we'll talk about master details, buckets, trees, and all that kind of stuff. How many of you in this room have used MongoDB? Okay, so I'd say it's about a third. Okay, so I'm going to assume that you've never seen MongoDB in your life. And so let's do some basic terminology. So who's used a relational database? Okay, all right. So you'll be very familiar with these terms. And here is a very simple mapping. Okay, so a table is a collection. A row or a set of rows is a JSON document. An index is an index. You don't want to change everything. Joins are embedding and linking, and we'll talk about partitioning with shards and shard keys in the second part after the break. Okay. So let's imagine we were building a blogging platform. This is a rough entity relationship diagram of what that would look like. You've got a blog, you've got entries for your blog, you've got many of those. Each one of those entries, you may have multiple tags associated with that blog. You might allow for commenting against each blog entry. And then the blog entry and the comment go back to a user and author in the system. Okay, so that's a fairly simple representation of a blogging system. So how would this look like in MongoDB? Well, we'd end up with two collections. One possible alternative is that we end up with two collections, a users collection and a blogs collection. And within the blogs collection, we have the entries and we embed our comments and our tags. So the key thing here is that what we've done here is we have taken a master detail relationship and folded it into a single object. Okay, so JSON allows you a very different and more flexible way to describe data. But you can also still retain the equivalent of a foreign key relationship through linking. Okay, so you don't have to represent everything as a hierarchy within a single object. You can still have access to regular associations. So what I'll do is I'll walk through a couple of examples, and I've got to write these slides. So for all my example data, I'm going to use my favourite book as a kid, which was Tintin's Destination Moon. So let's think about kind of what an instance would look like. So if you've never seen a piece of JSON, here's JSON, which is the JavaScript object notation. And it's a sets of name and value. So I've got an author attribute with the name of Hergé. I've got a date here, and I've got a full ISO date embedded within that. The text of this post, and then the first interesting thing is I have tags. And you see here, tags is an array, and it's got these two values in here. Okay, so I've now embedded an array of scalar values. So this is the kind of first form of how data is changing. So what does the query look like? So I've saved this object, how do I do it? So the syntax in MongoDB is really simple, it's very object-like syntax. So you do DB, which just dereferences your current database. Then posts, which is the name of the collection, then you do a find. And then the find will return you the object. Now what you'll see is we've actually added in this underscore ID attribute. So every object in the system has to have a unique identifier. And by default, the system will automatically generate that for you. You can override that if you want. If you've got your own unique identifier, you don't have to use the system-generated one. But that will be automatically added. It has to be unique, by the way. So the real power of MongoDB, because essentially we're all developers, we wanted something that was simple to use, that allowed us to retain the richness of a relational database without losing any of the scalability that we really desired. So one of the things that you can do is add a secondary index on any part of that document. So it's kind of cool that you've got the primary key, the underscore ID, that you can look up and query by, but sometimes I want to be able to kind of query by author. So what I can do is I can run the command ensure index and then build an index on author. So this is just a regular B-tree index that you'd see in your relational database. It's the same data structure, but it's allowing us to create these secondary indexes on any part of the data. So when I now do a find, and I put in the predicate of author of Hergé, I'm now using this index. So that index is going to be a more efficient way of finding this data. Okay? Questions on this so far? Okay, I haven't lost you all, right? As soon as I start seeing people keel over, I'll break for coffee and inject some coffee into you. Okay? All right. Like I said, we want to allow you to build rich applications without having to drop into the complexities of code. So there's all the operators you'd expect: in, not in, modular, size, exists, greater than, less than, and so on and so forth. So if I want to find a posts which have a tags element, I simply can do a post.find where the tag element exists is true. If I want to do the equivalent of a like expression, to do a wildcard, we've got an inbuilt regular expression parser, and so I can do an author where it's rooted with age, ignoring the case. Okay, so we can do wildcard searches as well. And there's built-in counting operators for you at the back, may be difficult to see, but you can do author per gain, and I can just count how many posts there are. Okay. So I've created an object. Well, one of the key things about MongoDB is that, quote, it's schemaless. Well, what that really means is that it's schema-free. And that means that each one of those documents can have a different set of attributes. So if I now want to extend this functionality, in our next sprint, we've decided that we want to allow people to comment against a blog entry. Seems a pretty cool thing to do. So how would we do that? Well, so let's talk about how we extend the schema. And so let us create a new object. So here's our comment that we want to add into this blog post. It's got an author, it's got a date, and it's got some text. So what I can now do is I can now update, and here is my predicate. So I'm going to update the post where the text is destination room. And then I'm going to use a couple of operators, the $push and the $increment. So the $push will push this new comments object, i.e. this, into the array called comments. We're going to use the $inc operator to increment this element called comments count by 1. Now, neither of those exist in our document already. And so what will happen as the consequence of running this update is that this new set of data is now added into your document. Okay? So here is our comments. It's an array. And we've now pushed an object into this array. So if you think about our tags here, we had an array of scalar values. Now this is an array of objects. So arrays can be scalar as well as containing objects. And down here we've actually incremented our comments count to 1. Okay? So our document has now changed. It's got a different set of attributes. And that's a very allowable thing from a database perspective for it to do. So now that we've extended the schema, perhaps we have some, one of the requirements is to start searching by authors of comments. Perhaps I want to see a widget of the latest, or latest comment by certain authors displayed. So what I can do is, we can go now and create an index on any part of that structure. So what I'm doing here is, I'm creating an index on the comments, and remember comments is an array, and then the .attribute. So that is going to be the attribute. I'll go back here. I'm going to create an index on the comments array, but the attribute within that array. So what that is going to do is going to traverse all the objects within this array, adding in an index value for each author. Okay, so you can build indexes at any part of the document structure. And so I can now do an efficient search on the comments.author, and there are a bunch of other things that we could start doing. So for example, if I want to find the last 5 posts, I can do a find, I can do a sort by the data sending, and then I can do a limit. So you've got all the kind of skip and limit functionality that you're used to in a relational database. And if I now want to find the most commented posts, I can do a sort on the comments count, descending, and limit it by 1. Okay? Yes, question?
The new index, there will be one index per database for all the authors, or will there be separate indexes for each block entry and the authors within that?
So there'll be one index created So each time you insert a document, we'll analyze the data values and add those values into the same B-tree index.
Okay, but there will be one for the whole database.
There'll be one for that collection. So you create the index for each collection, just like you create indexes for tables. Okay. All right. So how do you do this from the code? There are a whole bunch of official drivers we support. So what's the kind of who's using Java? Fair amount of you Python. Fair amount of you Ruby. What have I missed out? What else is people using? Node, okay. All right. There's also some object data mappers, and we'll talk about these in a second. So if you want to be able to use annotations, for example, you can still use that. There's a whole bunch of community drivers. So if you're using F# or Smalltalk or Delphi, or I think there's actually somebody creating one for COBOL. I have no idea why, but there's something to do with that. Okay, so how does this look like if we're manipulating this through Java? Well, it's really dead simple. So I've got a collection object, and what I do is I want to get the database called posts. I then create myself a map, which is a new hash map, and then I start adding in these attributes, the author text and the date. And then to insert that object, I just say insert, and I instantiate an object from the hash map. Okay, so it's really, really, really simple. If you were using one of the object mappers, and this is again an example from Java, you can use annotations, so you can describe your class as an entity, you can describe the IDs, which ones are indexed, and so on and so forth. So if you're using annotations in Java, there are ways that you can carry on doing that, mapping your object down to its persistence layer. And if you were using Morphia, for example, how do I now create an object? Well, I go create a new data store, and then with my post class, I create a new post class using the constructor, passing in values, and then I say data store.save, that entry, and I'm done. Okay? So the idea is that it's supposed to be very, very simple to use, regardless if you're using Java, or Ruby, or Perl, or PHP, or Node. Okay. So that's really basic stuff. So let's talk about some common patterns. And patterns are lovely. It's a lovely pattern. I think it's some kind of cactus. Very pretty. You have a nice moment of enjoying the prettiness. Okay. Inheritance. So let's talk about inheritance. That's a common pattern. So here's a typical form of inheritance. I've got a shape, which has got an area attribute. And I've got a couple of specializations of circle, square, and rectangle, which have got a different set of attributes. Okay? How would we represent this in a relational database?
There are at least two ways how to do it. You can have single table inheritance or multi-table inheritance.
Yep. It's all kind of a bit, you'd end up, this is one example of how you do it. Yeah. Here is a single table with a discriminator column, which describes the different types, and then we have a whole bunch of columns which are all nullable with values in. So if I now query this, I've got to now know that circle actually doesn't have a length and width, okay, and a square doesn't have a radius. Well, that's really, really obvious, but if you get to more exotic data types, you get these very, very wide tables. If you look at an SAP schema, this would be called A1, this column would be called A2, this would be A3, A4. So people start building these very abstract schemas with a layer above the abstract schema to describe how the data is used within inside it. And I've built a lot of those systems myself, and they're very complicated to debug at 3 o'clock in the morning. Okay, so how would we store this data in MongoDB? Well, we simply create 3 documents. We probably still need a discriminator, but then we simply store just the attributes we have for each one of those instances. So if you look at the circle, we have the area and the radius, and that's all we have. The square, we just have the area and the length. So you only need to store those attributes you actually need for that particular instance. Now, if I want to find all the shapes where the radius is greater than 0, Well, only radius is applicable in this particular document. So when I do a query that says radius greater than 0, it's going to first see whether this has got a radius attribute. It has. Is that greater than 0? So that matches the predicate, so it will be returned. These next two documents don't have a radius attribute, and so therefore are not even included in the results. So you get a very natural way of manipulating that data. I can now go and create an index on this radius. So if a very frequent query was to do radius greater than 0, I can now index the radius attribute, and I can create a sparse index on that, which means that I will only store values if the radius is actually present. So you can build very, very small, highly focused indexes just on those data elements. Okay, inheritance makes sense? Okay, all right, one to many. Okay, so one shot, many fish. If we're looking at our, going back, we've got our blog and our comments examples. So the thing about relationships, if you look at a relational database, which will be represented with a foreign key, they're describing the degree of association, they're describing the containment and the life cycle. So for example, on a foreign key, you can say delete cascade. So if I now delete the master, that means all the children or the details get automatically deleted as well. And so essentially what you're trying to describe in a relationship is those attributes. So there's two basic ways that you can actually represent this data in MongoDB. The first is through embedding. And so what we've done here is that we have taken our master and a detail, which is our blogs and our comments, and we've taken the comments and we have embedded them within the post document. Okay, so this one document describes the master and all the details. All the details will be embedded within this document. So this is kind of really good because that means in one round trip to the database, I've managed to get the blog and all the comments associated with it. Okay? So that's pretty neat. The other alternative is linking. So I could actually normalize the posts and the comments into two separate collections and have an ID, so the comments no longer contain all of the data, they simply contain a link to the comment that's associated with it. Okay, so this is very much kind of looking how you'd traditionally implement a master detail in a relational database. You have a matching key in a relationship between them. Now what this does mean, if I want to now find my comments, and my posts and my comments, I now have to execute two queries. Right? So MongoDB has no joins. Okay, so if I now want to get both sets of information, I now have to execute two queries. So,
wouldn't it be better if we use the DB references?
they're exactly the same.
So there's no difference.
There is no difference.
So there's no reason why would I use the references?
None at all. Okay. Okay, so if I was to characterize embedding versus linking, so embedding, it means that if you think about what's happening on disk, you've got the head's got to seek once, and then it does a big sequential read to read all of that data. So that means that you can get that data in one round trip, and the read is going to be relative to the size of that data. So if that data is 50 bytes, then we can pull on that data by reading in 50 bytes. If that whole object is 20k, you've now got to read 20k. Okay, so both the reads and the writes are going to be relative to the size of that object because you're reading and writing the whole object. Now with linking, you've got one seek on disk to read the master, but then you've got a seek for each of the details that you then have to read. And you've also got two round trips. But it means that the reads are longer but are consistent. And so the writes are longer but they're also consistent as well. So there's no real right or wrong between should I do embedding or linking. It really comes down to what is the data that you want to manipulate, and what is the pattern for reads and writes and updates and how you want to manipulate that data. What you've got is you've got two alternatives which have different performance characteristics.
By consistent you mean like constant time?
Yes. Okay. So how do I represent a many-to-many? And then we have many dolphins going after many fish. So here's a typical many-to-many. So we've got products and we've got categories and we have some intersection entity between that. So that means any product could be in a number of categories. So for example, my Hergé novel could be a comic, but it could also be a movie. And our category of movies could also contain our Hergé movie, our Tintin movie, as well as all the other movies that we have listed. So one alternative approach to this is that we, in our products table or collection, we list all the IDs for this particular product. And then the categories then have a product ID that goes back to the products. So in effect what we're doing is we're storing the association at both ends, which is kind of what happens in a relational database. Now the downside of storing this relationship at both ends, well the upside is that I can query from categories back to product, and I can go from product to categories. That allows the bi-directional traversals, that's good. But it means that if I now want to delete this product, destination moon, what do I need to do? Well, what I have to do is I now have to go through the categories and remove it from this product list. Okay, so that means that you have to do, because you've stored it at both ends, you now have to maintain both ends of the association. So as an alternative to that, what we could do is, so that's just how we go and query the categories. As an alternative to that, what we could do is we could just store one end of the association. So we'll store the categories for the products, but we won't store the products for the categories. Okay? So that now means that if I want to find all the products for a given category, it's really simple. I can just do a find of category ID equals particular ID. If I now want to traverse the association the other way, I have to execute two queries. The first to find the product ID, and then the second to do the find with a $in. Okay, so those are decisions that you make in terms of when you're building your schema or designing your schema with MongoDB. It really comes down to thinking about patterns of data usage and how you want to use them. All right, so the next one to think about is trees. Okay, so that's a picture of a tree and a nice melon. And so if we look at our blogging application, we want to be able to now allow not only comments to be recorded, but people to reply to comments. Okay, so this is going to be a natural kind of hierarchy of information. So typically the first time people see this problem in MongoDB, they'll create a structure that looks like this. Here's our comment, and I want to have the author of the comment, and then I want to have the replies to the comments, which again is another array of the person who replied to it, and then within the reply you have another array of replies. Okay? Anybody see a problem with this?
Okay,
Well,
index is harder.
Building an index is harder, but what we've created is this is an arbitrarily deep tree within a single document. Okay? So if we said we could only have 3 levels, then it makes searching really easy. But if you allow any number of levels, you don't know how deep to go down. So whilst this works, and it's a very natural way of thinking about your data, it's going to cause you many issues. So what's an alternative for modeling of that? So if we look at our kind of our replies and our comments with this tree at the top, what you can do is you can store the ancestors of a particular node. So for B, its ascendant is A. If we look at C, C is B and A, but it's a direct reply to B. So you can start modeling parts of this data structure like this. So once you do that, it's fairly easy to build some powerful queries. So if I want to find all threads where B is in, it's simply just a question of finding where the thread is equal to B. If I want to find all the replies for E, then I can just do reply to. And if I want to find the history of F, I want to start here and I want to walk up the tree, then I've got two queries I need to execute. One is to find the ID of F, and then the second is to do a $in on the threads where F is part of. Okay? So you've got a fairly simple way of describing that hierarchical data. What this form of the data will allow you to do is to build something of arbitrary depth and still maintaining some very simple query semantics. A third alternative for trees is trees as paths. So think about file system hierarchy. So again, I could store this as a flat level, but then with the path indicate that tree of data. Okay, so that's just another way you can do it. And this allows you to do simple things like use the wildcard expressions or the regular expressions to find a part in that tree. Okay? Makes sense, and I know I'm going a million miles an hour, and I'll give you these slides afterwards. Okay, so finally, or last but one, queues. So how would I do a queue? So let's say I have got a list of jobs I want to execute. I can actually store some state information, whether the job is in progress or a priority. And so right now I can use a special operator called find and modify. And what this will do is it will go find the document and update that in one atomic operation. So if I now have multiple threads that want to go and pick up the next job to execute, I can use find and modify. So the query will look for where the in progress is false. I'm going to sort by the priority descending. So I'm going to find the highest priority job. And then for that first document I find, I'm then going to execute an update. So I'm going to set the in progress to true because this job has now started. I'm also going to add an attribute of started so I know when this started. Okay. So with this simple kind of this find and modify statement, I can now have multiple threads executing, picking up the next job in the queue and ensure that there is the correct concurrency between those jobs, because that's an atomic operation. And so how would you put this all together? So let's take a use case of an inventory system. And a typical use case for inventory is that a user has a number of votes, or you have a finite amount of stock to sell, or a resource that can only be provisioned a number of times. Okay? So what would that schema look like? So let's say we were doing votes, and we've got a user, here's how many votes they have. So imagine this is Stack Overflow or your favourite blogging voting platform, and what I've voted for. And so if I now need to subtract a vote and add what I've voted to, I can simply do a single update statement. So I want to search for where the ID is me, where the votes is greater than 0, so I still have some votes to vote on, and I voted for is not equal to destination moon. I can only vote for a blog once and only once. Okay? And if I find a matching document, then I can push the voted for, and push destination moon into this array, and then I can decrement the votes by 1. Okay, so again in a single atomic operation, what I have managed to do is maintain a finite resource, which is the votes, and ensure that somebody votes and only once and only once.
The not equal operator won't use index, is that right? The not equal operator won't use index.
Correct. Well, this is the not equal operator in 2.0 works differently. And so we'll translate a not equals to a greater than and less than, right? Which means that we can still use the index. Okay. All right. So this is a picture I actually took today at the zoo. And so here are things to not try. or if you do try them, things will be very bad for you. So, just like a relational database, get your indexes right, which means that don't have too many indexes and index the right keys. And the most frequent cause for a performance problem, just like a relational database, is frequent queries that don't use an index. Okay? As we talked about earlier, having large, deeply nested documents are going to cause issues not only with maintaining that data, because you're reading and writing very large objects, but also querying some of that. So that goes back to our hierarchical query. We often see sometimes people have a single collection, and they put every single possible object in an entire system into a single collection. This is very possible, but it means from your application code says, look, read from this collection, write from this collection, and you have to have a lot of context in your code to make sure you're doing the right thing. Simply putting things into different collections, there's no performance penalty in doing that. It will make your code far simpler to understand. We also sometimes see people creating a collection per user of the system. There's a limit of 38,000 or so collections in a single system, so you'll hit a hard limit on that. If you want to have some, if you're doing, for example, a multi-tenancy system, it's much easier to have a discriminator attribute rather than create a new collection for each user or each tenant in the system. Okay. Quick summary. So, schema design is different. There are a whole bunch of blogs out there. There's a whole bunch of really good, practical solutions for basic problems. But the basic data design principles remain the same, which is you've got to understand the data, the relationships between the data, and as importantly, how your use cases work with that data. So traditionally we had, our data architecting as a separate thing from our application design. What we have evolved to is a model where you need to do a bit of application design with some data design and iterate frequently over that to quickly get to the right answer. And so focusing on how the application manipulates data will give you a more performant schema faster. You can rapidly evolve the schema, so you can add new elements into the documents, not only just for polymorphism, but for example, you're doing an application upgrade. You've got V1 of your code and V2 of your code. So you can allow that data to coexist. So in a traditional rollout, when you're rolling out the new version of your application, you normally have a schema upgrade script, which you cross your fingers and you hope it executes. Otherwise, your data is you hope you then have a good backup if anything goes wrong. Now, what we've seen people do is take the advantage of polymorphism to allow them to do upgrades in place. So instead of doing a forced migration, what they'll do is they'll push the new code, and the first time the object is touched, do an upgrade in place. So it allows you to take the cost of a data upgrade and cost that over time, rather than doing it in the night of the release of the code. And this final one is that you have lots of new ways to shoot yourself. And so you make some of those choices and make them wise. Okay. That gets us quite neatly about 10 minutes behind, but on to part 3. So I think we're now scheduled to have a quick coffee break. I need a coffee break. And then we'll talk about scaling with MongoDB. Okay?
than using active record.
Yeah, I mean,
I have to learn, so give me a slow start. Real benefit is when the scaling Maybe you guys want to ask something.
Context searches, so right now we're going I think that basically tokenize the text inside, and then there's one biotech companies because they need that. They can describe their things in 2D. I think there's at least one because they can use the XY coordinate system to give relative distance. No questions. So, I think we've essentially tried to solve MongoDB is all about objects being modified to deal with just synchronization. So typically mobile devices. And so they make so they